Okay, today we're going to look at sequences. Now, a sequence could be images, like this one, or numbers in a sequence, where the idea is we're looking for maybe a pattern that tells us how we can anticipate what the next image is, or extend that pattern to, say, the next image and extend it to the next image. In a case like that, where we want to extend the pattern to the next image and use that image to go to the next one, that will be a recursive formula for the sequence. In other cases, we might not be interested in the next image. Maybe we're interested in the 15th image in the sequence. So if we wanted to jump right to a very particular value, that would be an explicit formula. So this video is going to be about the recursive version of a sequence, and you can watch another video of mine for the explicit. So we're going to explore this. Now, with these images, I could say that this is the first image, the second image, the third, fourth, fifth, right? And for a recursive formula, we'll extend the pattern to say, well, what would the sixth image look like? And then if I can use the sixth image to find the seventh image, and the seventh image to find the eighth image, that's exactly what the recursive version would be. Now, generally what we'll do is, since we're trying to find the patterns, I can say, in the first image, there is one block. In the second image, there are 2 blocks. In the third image, there are 4 blocks. In the fourth image, there are 7 blocks. And I can maybe list the values instead of looking at them as blocks, because the blocks will be very cumbersome and time-consuming to make. So a lot of times what we'll say is we'll let n be which image we're looking at. A with a subscript of n will be the amount, in this case, of blocks in that said image. So we can see the pattern, right? We can anticipate what the next value would look like. So we could do this visually, but we're going to explore it a little bit more on just the numeric sense, and it'll make it a little easier to work through this because we'll look for the patterns of the numbers rather than the bulky boxes. So let's look here. So there's a number of different sequences that you might have explored. We could say that maybe to get from the first image to the second image, we will add some number of blocks to it, and then the second to the third, add some number of blocks. We could also take away blocks. We could multiply the number of blocks. So really, when you're looking for the pattern, you can try adding values, multiplying values, and then depending on what you have, we can move on from there. Now, these images, by the way, we're going to look more specifically at. We're going to look at the sum of values. So, if we look here at the first image has 1 value. If we add 1 value, we'll get the second value. If we want to figure out what to add to 2 to get 4, that would be plus 2, right? And then we could add 3 blocks to get to the 7. We can add 4 blocks to get to the 11. Now, if you're familiar, if these differences between the number of blocks were all the same, that would represent a linear function. A linear function grows at a constant rate. So if it was add 1 block, add 1 block, add 1 block, add 1 block, then the recursive formula would be very easy. We could take one image and just add that number to get to the next one. But we don't have that. So this isn't a linear function. So what we're going to try to do is we're going to look at, well, how are these growing? So if we look at these differences between the images, we can see that this guy is growing by 1, this guy is growing by 1, this guy is growing by 1. So what we'll do is we'll call this first set of growth values the first difference, or the first order difference, as you might call it. This second set of values would be the second difference, or you might call it a second order difference. So if we think about what's happening here, the number of blocks is changing, of course, but the rate at which it's changing is linear. It's growing. The growth is at a constant rate. So when we're putting together our recursive version, we can say that it's always going to be, we need to start at some value, right? Even if it's growing, we need to know where to start growing. And then what we'll do is we'll say that if we want one of the images, then if we take the value before it and add something to it, then we'll get to the next image. So kind of like I was saying, if we had a first difference that was constant, +2, +2, +2, +2, then we could take that difference, take that term, add that value, like +2, to get to the next one. And then if we add another 2, we'll get to the next one. That would be a linear sequence, right? Here, though, like we said, our growth isn't constant. So this isn't going to be a constant. Our growth is linear because it's starting off with a growth, and then the rate at which this growth is occurring is constant. So what we're adding is a linear growth. And if you want to say a linear function looks like mx plus b, then we can take the value, add a growth that is linear, and it will build this sequence, right? So if the first order difference is constant, then that's going to be linear. If the second order difference is constant, then that's going to be a quadratic. So we have a quadratic sequence of values. Okay? So this second difference is the rate at which the growth is changing. And in a linear function, m is the slope or the rate of change. So this second difference is going to be our m value. So what I'm going to do is I'm just going to use this like a formula, and I'm going to plug values in because we want to make this thing. So the m is that second order difference, which is a constant, so it's growing at a rate of 1, right? Now we can use x, like mx plus b. Since we used n's, like the number of values, then we can say that x is the same thing as our n value in terms of mx plus b. Okay. Now, the way the sequence worked was we can take a value, add something to it to get to the next value. So, for instance, if I wanted to take the first term, now the value of the first term was 1, so if I wanted to take the value of the first term, I can add something to that to get to the next term, which would be the second term. So the value of the second term is 2. So I can get the second term, right, by taking the first term and adding some value, right? Because if I wanted n to be 2, which is the value of the second term, then 2 minus 1, which is the value of the first term, a sub 1, right? Now, in this case, n is 2, or x, so I'm going to plug in for x a 2, because I wanted the second term. Now, b we don't know, so I'm just going to leave it as a b, but now we have this equation with enough information to solve for the only unknown value, which is our b term. So I can do order of operations and get b by itself. So we'll say 2 is equal to 1 plus 1 times 2, which is 2, plus b, right? And then I can combine like terms. 1 plus 2 is 3 plus b. And if I want to solve for b, then I can subtract 3 from both sides. So negative 1 is b. So the b value of this growth rate is negative 1. We have this value. We know that the linear growth here has a rate of change of 1. So I'm going to plug in my b, I'm going to plug in my m, and that way I can make this formula. So the recursive formula, which needs to start at the first term. So our first term was 1. And then we can get any term we want by taking the term that comes before it and add this linear growth in which our growth rate is 1. So if I want to say 1n, right, I'm going to use n instead of x because I used n's here, plus our b value, but our b value is negative 1. So I don't have to say plus a negative 1. I can just say minus 1. So here we go. Now, if we're not sure that we did it right, we have a set of values from our sequence which were given. So if I wanted to start with the first term, I can use the first term to get to the second term. I can use the second term to get to the third term, and so forth. So let's kind of go down the line. If I wanted the second term, right, so n would be 2, I can find the second term, right? I can find the second term by taking the term before it, which is a sub 1, but a sub 1 we said was 1, and I can add a 1n, n was 2 minus 1, right? So 1 plus 2 minus 1 is 2, which matches. And if I wanted to try the next value, right? If I wanted the next value, let's say the third term, I can say I can find the third term by taking the term before it, which was the second term. That's this guy. This is a sub 2. So I can take the second term, add 1n, so 1, and this case is 3 minus 1, so 2, 1 times 3, minus 1, so what's that? 5 minus 1 is 4, so the third term is 4. Yeah. So there we go. We got it. We got the, I mean, you could keep trying them if you're, really curious, but there it is. We got the recursive version of this sequence. All right? Let's try another one. So, if you're given images, we can always take the images, count out which image we're looking at, and then the number of blocks that we have. Now, in this case, having like -3 blocks doesn't really make any sense. So we're just jumping right to the idea that we have a sequence of values, and we just want to see the pattern numerically, right? Now, just like we did, if we wanted to just call it x, then this would be the function value when we had plugged in x. So if you're, used to function notation, we can still use that notation. But nonetheless, we want to see the pattern. So the pattern is either going to grow by adding or subtracting or multiplying. We'd have to kind of visualize that, right? We'd try things out. But generally, we'll try adding values together. So we can say, well, what would I add to -3 to get to 3? Well, that'd be 6. If I wanted to add something to 3 to get 13, that'd be 10. If I wanted to continue adding, then we could do that, right? So again, first order difference is not a constant. Obviously, this isn't a linear function, but we can check the second order difference. The second difference here between 6 and 10, I would add 4 to get from 6 to 10. I would add 4 again. I would add 4 again. So it seems like we've found a pattern. So again, since this is a second order difference is a constant, that means this is a quadratic function. And a quadratic function, right, remember, is built by saying we can find a term by taking the one before it and adding some linear component, right? X's, N's, whatever you want to do, right? We're just seeing what's supposed to happen, right? The 4 is the rate at which the growth is happening. So I'm going to put that in here, right? I can pick any term I want. If I want to pick the 5th term and say, I can pick 45, which came from the term before it. It doesn't matter, right? These values is how the sequence will grow. So depending on which ones you pick will depend on what X is, or N, right? I'm just going to keep the number small, right? Because I already see the pattern. I don't really want to work with bigger numbers. So I'm going to say I'll find the 2nd term, which is 3, by taking the term before it, the 1st term, which is -3, and adding this linear component. Now, if I utilize the 2nd term here, that means N, or X, in this case, is 2, so I'm going to plug a 2 in here. If I would have used 13 and 3, for instance, if I put 13 here, that means that X, to make that value, would have been 3. I would have changed that to a 3. So just be careful, whichever one you pick, that X or N, whatever you got, needs to match these values here. B, of course, is something that we do not know, right? But now we have enough to solve for B. If I keep the 3 over here, I'll do multiplication first. 4 times 2 is 8, right? Then we can combine like terms. I can say -3 plus 8 is 5. Subtract the 5. So -2 equals B. So we'll build our recursive version. Remember, don't forget the 1st term. The 1st term is where we start, which in this case is -3. And then from the 1st term, I can get to the next term by taking the term before it and adding a linear component. The rate at which this linear component is increasing is 4, right? Since I used n's here, I'm just going to use an n here. Plus b, but b was -2. So there we have it. If we want to check it, like I said, we can go down the list, plug in the 2nd term to get the 3rd term, plug in the 4th term to get the 5th term, use our n's. We can do that if we wanted to. I'll let you try it if you really want. All right, let's try one more. Okay. So again, I have the sequence already made for us. I don't have images. If I had images, I can build them up, right? If I had X and Y, or N and A of N, right? Any of those is fine. Okay. I'm going to utilize a different notation here, so I'm going to go back to the f of x, right? So even if you were given x and y, I'm going to utilize a different notation here, just to familiarize yourself with what answers could look like. But again, I still need to figure out how this sequence is being built so I can anticipate a pattern to it. So I'm going to try adding and subtracting, right? So what would I add to 6 to make it a 5? Well, I would actually add a -1 or take away 1, right? Again, how would I get from 5 to 0? I would actually subtract 5. And then I would subtract 9. And then I would subtract 13. So the numbers could go down. There's nothing wrong with that. They're all not the same. So again, it's not linear, right? But now I want to see how to get from this difference to this difference. This would be subtracting 4, subtracting 4, subtracting 4. So since this 2nd order difference is constant, I know that my growth is linear. This represents a quadratic function. Okay. So again, kind of like I said, I'm going to use a different notation here, right? I can say that I can find a term that I'm interested in by taking the term before it, right? So if I pick an x, x minus 1 would be the term that came before that x value, right? So you can utilize function notation if we want, and it would still be a linear increase because the 2nd order difference is constant. So f of x and f of x minus 1, a of n minus 1. These are going to represent the same sets of values, right? Okay. So again, our second order difference is negative 4. So I'm going to plug in a negative 4 here. Right? I'm going to select any x value I want, which will match up with these terms here. So again, I'm going to take the second term. So the f of x value will be 5. The f of x that came from the x before it would be 6, right? If I want to say plus the negative 4, I mean, I could do that just to keep with that. Now again, this function value was 5 when x was 2. So I'm going to plug in a 2 here. And again, I don't know the b value, so I can just leave it as a b. But we're back to the exact same thing we did despite the notation. So I can say 5 is the result of 6. Negative 4 times 2 is negative 8. So I'm not going to say plus a negative 8. I'm just going to write the minus 8. Plus b. And then keep combining like terms. 5 is equal to 6 minus 8, which is negative 2. And if I want b by itself, this time I'm going to add 2. That's fine, whatever we got to do to get b by itself. So 7 is equal to b. M was equal to negative 4. And then we can build our recursive version. So we still want to start with the first term. So in this case of f of x, this would be, f of 1, which is the first term in our, sequence here, which is 6. And then I can find any function value by taking the value before it. Now, if I want to say plus a negative 4, because m is negative 4, that's fine. Or I'll just say minus 4x as a product, plus b, but b was 7. And again, if you want to try it, we got different values. We're using different notations, so we're not really sure. We can just remember it, because this builds it one step at a time. So if I wanted to check this guy, I would actually have to, either start here and build it, or since we had the sequence, I could actually just utilize, like, all right, if I plug in negative 9 here, I better get negative 22 out, right? So since we have these values, we can jump down to here. If I wanted like the 8th value, since I don't know 6 or 7, if I wanted to check the 8th value, I would have to find the 6th by using the 5th term, and I would have to find the 6th by using the 7th by using the 6th term, and so forth. Right? So here we go. So finding recursive, right? Again, like I said, if we wanted explicit form, I'll make another video of that one. You can watch that. All right?